Again, good morning and welcome to Physical Science 1. We're still doing the live sessions basically. And I'm recording this session for the sake of the people who cannot make it. Today's topic is going to be on fluids. We covered basically so far, in a sense, solids, because Newton's laws, when they talk about point particles and object, they mean with them that they don't change shape. Albeit the third law allows for the possibility of the mass changing, meaning that if the mass is, for example, added continuously to the system, then in this case we don't talk about the speed of the system as descriptive of the motion, we talk about the momentum, which is the combination mass velocity. So that helps us save that situation. Or for example, in the case of an explosion, or for example, in the case of the taking off of a rocket, for example, that it is losing mass continuously because of the fuel that it's consuming and escaping in the form of gas. So those are, in a sense, what the three laws describe. Then there is another branch of physics that we didn't delve in it very much, but it's that of the solids. Solid is thought of as the assembly of more than a point object, basically. If you have 1, 2, 3, 4, 5, and they constantly keep the distance between them. You take any solid, for example, this object, the distance between this point and this point is the same no matter where the object moves, this way, up and down. This is called the rigid body because the structure of it is not changing. Fluids are not rigid though. Like water, for example, one end of the water can separate from the other end. Actually, they move apart. So the fluid is not a rigid body. A gas also is not a rigid body. So we needed another physics to really describe this kind of objects that don't retain their form, if you wish. They don't retain the distances between their different components. Their components move in and out of one another, okay? So that's basically how you don't have to necessarily compress them. Okay, for example, water is not easily compressible. It resists the compression. But you can take parts of the water and move them away and bring them closer together, put them in a smaller container and they get closer, put them in a big container and they separate. So the word compression sometimes is confused with what we're talking about. As a matter of fact, most of the things we talk about in terms of fluid dynamics and is in terms of what is called of incompressible fluids, fluids that not necessarily compress easily. Then we come into the real situation where the fluids are actually compressible. There is a small fraction of them. And this is not true only for fluids. You take this object, for example, and if you press it hard enough, you're going to basically change its volume. So this, no matter how rigid the body is, it still has some components of rigidity. So this is just an introduction basically of what this thing is. In this week, I sent you also a reminder of what we're going to be doing first, and I posted everything on the model, and also what is due. So please pay attention to what is due. We don't want to fall behind basically in terms of due dates. I think I graded everything that needs to be graded that is due up to this point. And please review the rubrics. All of the grading is following rubrics. I do not assign anything without rubrics, with the exception of quizzes that don't have rubrics because they have built-in rubrics. Their grading is based basically on the points there. Sherry raised a very good point earlier, and I was actually thinking about it, that I think the time allotted for the quizzes is a little bit short because you barely have a minute to complete a question, and that's probably not enough. So I'm going to revise that. Actually, I was thinking about it. So that you'll have more time to actually consume the question and hopefully answer it correctly. So that's one of the things I'm going to do. If you guys don't see it, please send me a reminder again that, hey, you promised to do something and you didn't do it. Can you please take care of it? So I'll do that, okay? Sometimes you get basically sidetracked with other things. So please pay attention to what is due this week because it's very important. Like I said, I want to really stick to the schedule as much as possible. We don't want to be changing things. Let's get into today's topic, which should be, let me first of all find it. Fluid mechanics, here it is. Okay. Does everybody follow with me here that we are looking at this PowerPoint that says fluid mechanics? Good, Jacqueline, thank you very much. Thank you, everybody. So basically, like I said, this is a new, basically a different type of physics that we need to obey to study it. You have to understand even this physics for fluid mechanics really underlyingly, because if you take every single point of that fluid, it still obeys Newton's laws of motion. So this did not escape the three laws of Newton, basically the law, the first one that if any component of that liquid is not under any net forces, it's going to stay in its place, then or move with constant speed, or if it's under net forces, it's going to accelerate, change its motion, namely with an acceleration that is proportional to the net forces divided by its inertia divided by its mass. And the third law, that if it interacts with something else, it's going to do so in such a one, if one attracts the other, or the other one attracts it back with the same and equal amount of forces, and vice versa if they are repelling one another in the same direction. So the three laws of Newton, they're still valid in here. But this is what is called a macroscopic description of the fluid. I mean, if you take a fluid, I don't have my cup of water in here, and you look at the fluid and you see it in general. You see a cup of water and there is water inside. And if you put a coloring fluid in it, you will see basically the coloring fluid will start to spread until it settles and basically fills the entire liquid. And at that point, it looks like the liquid is not moving, is not going anywhere. It's staying in its place. Unless, of course, you pour it, then you will see the coloring fluid moving. So we're going to assume initially that we're dealing with what is called a static fluid, fluids that don't move. Okay, fluids that you put them in a cup and they don't move. So we need to describe those fluids. We need to come up with quantities, because again, if we don't come up with quantities that we append numbers to them, we are not describing them. We're basically, it's not physics, I should say. Okay, physics relies on experimentation and observations. And the two quantities, and only two quantities so far for the static fluid that we will need, are the density of the fluid. That distinguishes a fluid from the other. You take a fluid, for example, water, and you take another fluid, it doesn't matter which one, for example, salt water, for example, that's another example, or for example, oil, or whatever other fluid that you have in mind. And you take the same volume of them, put them in the same bottle, for example, and weigh them. You will find one fluid weighs differently than the other. So density now plays a role. How much fluid I have for the same volume. So that's what the density is. So now, instead of talking about water and oil has this much, for example, concentration of whatever additive it is, and the other one does not, and there is, so I can just refer to a number, append a number to them from now on, saying this fluid has this much density, and this fluid has this much density, and this fluid has this much density. If I can find a way, a standard way for me to measure the mass for a given volume of every single fluid. So from now on, we have a number appended to each and every one of those fluids. A good reference in here, and it's a very important reference actually, and it's worth remembering no matter where you are, the density of water is known to be kilogram per liter, okay? That is a unit that it's worth remembering. If you bring me 1 liter of water, it weighs 1 kilogram. So that's a number to remember. It's a 1. Or a ton, 1,000 kilogram per cubic meter. It's the same thing. 1,000 kilogram per cubic meter. So this is a number that is worth remembering. Okay. I know some of you probably prefer other numbers like your birthday or the birthday of somebody you love, or your social security number. Stick this number next to them, okay? Put this number there, 1,000 kilogram per cubic meter. So from now on, if we ask about the density of water, this is water, not anything else. Okay, it's 1,000 kilogram per cubic meter. That's in the standard units SI, or 1 kilogram for each liter, okay? So there is a correspondence between a liter and a cubic meter. 1,000 liters is a cubic meter. That's another thing in there. Or is it? Yeah. Yeah, okay? So that is something that is worth remembering. So the first descriptive of fluids is this thing, which is the density, okay? And we're going to talk more of definitions of what it. The second descriptive of a fluid, because I could have the same water, and if I bring, for example, a 1 liter of water, which weighs 1 kilogram, and for example, bring another cubic meter, which weighs a ton, which weighs a kilogram, 1,000 kilograms. And if I put my hand, or if I put an object, for example, or if I actually go inside of this, I will feel different numbers in here. And the second different number is the pressure the fluid exerts. Obviously, the 1,000 kilograms on a given area will exert probably more pressure than the 1 kilogram. But if you change the areas now, if you take the 1,000 kilogram and lay it on the asphalt, for example, in the parking lot, it will not exert as much pressure. For example, if you take a bottle of water and put it, a bottle of 1 liter of water and put it on a smaller area. So in here, the pressure is related to basically the concept of the area. How much an area the fluid is basically subject to. So in this case, the area plays a role. So that's another descriptive for your wish. For the same fluid, it may have different pressures. So the second descriptive that we need in here is the pressure. The pressure, as you have guessed already, is a force, which is the weight in this case, divided by an area. So it has the units of the force, which is in Newton, divided by the units of the area, which is just the distance times distance, which is meter squared. So those are the two critical concepts that we will need to describe fluids. For example, when we talked about object, mass, acceleration, velocity, and all of that, describe this object from the next, and then we appended number to them, and we were smart about describing them with those numbers. Now we have other measures basically to describe fluids, static fluids that is, using the concept of density and the concept of pressure. Later on, we will talk about the buoyancy, which is a force exerted by fluids on any object that is inside of them, okay? And then we'll talk about Archimedes principle, that is basically how we measure the buoyant force. And then we will move the concept of density from that of a liquid, which we, I mean, if you hear me say the word water, that is really, in a sense, is what I mean by liquid. So all liquids, oil, whatever you have in mind, is the same thing. So sometimes we refer to them as water, but we mean in all kinds of liquids. Well, gases also are some sort of liquids. They have different properties. Gases occupy the entire volume that you give them. So whatever volume they want to, you give them, so they occupy, but the others, they don't. That's the only difference. It's a slight difference between them, but they exhibit the same properties. You will need the density for the air, and you will also need the pressure that the air exerts. So that's the other concept. Then we'll talk specifically about the atmospheric pressure and how it's related to day-to-day experience, especially, for example, when it comes to climate and weather. So that's an important concept. And then we'll talk about Pascal's principle for the hydraulic press. Again, using still statics, fluids are not moving. And then we will talk about buoyancy again, in the case of the air too. Same thing, like I said, everything that applies in fluid applies in the gas. Finally, we will promote ourselves and move from the situation where fluids are not moving, to fluids now in motion. To moving fluids, if you wish. If you have, for example, a stream of water moving in a riverbed, for example, that is what I mean by that. So that is now, we're not talking about a cup of water or a bottle or, for example, a pond or anything like that. Now we're talking about water that is in motion. That is governed by principle of Bernoulli. There are two types of motions. There is the streamline, basically, which is the smooth motion of fluids. And this is a motion that is governed with more or less constant speed, or constant flow, I should say, where the flow depends on the cross section. If you take, for example, a hose of water and you have the fluid coming off of it, but if you squeeze, it's the same fluid that left the faucet, went through the tube, and now it's squeezed through. But at some points, it appears to be moving faster. So that's really what Bernoulli's expression in this case is, deals with how fast the fluids move, and the pressure, and so on and so forth. And as an example of, I mean, we're not going to delve in it. There is another kind of behavior of fluids that is not at constant speed, but it becomes more chaotic. It's called the turbulent fluids, and that is, for example, turbulent weather and turbulence in general and things like that, like what's happening, for example, on the weather on Jupiter, but sometimes even in here on Earth. So this is basically in a nutshell what this chapter is, and we're going to get into the details of it. Any questions so far? No? Okay. Again, the concept of density is an important property of materials. This is a concept that does not depend on the size of the object or the mass of the object independently. Basically, if you take 1 kilogram of iron or 1 ton of iron, they both have the same density. What happened in this case is the 1 kilogram will occupy probably this much space, 1 ton will occupy this much space, so that the ratio of the mass over volume in this case stays the same. So this is an intrinsic property of objects, okay? So it doesn't matter how much matter you take from that object, they have the same property. So this is a description, if you wish, of the object itself. So it's a measure of the compactness. So this is what we people call sometimes how heavy and light the object is, but it's really more of a measure of a ratio of two quantities, okay? Can you guys excuse me for a second? This guy comes in here to cut the grass, so I'm going to go and basically make sure the window is closed, okay? Sorry about that, okay? He comes in all the time in the morning and makes a mess and leaves. Anyway, so basically the density, as I was saying, it's a property for all materials. One of the things that you do in the physics lab, if you have had a chance to do that, is sometimes determine the object. I mean, you have a compound. It's a physics or chemistry sometimes. This is not unique to chemistry, where you're given an element and you don't know what it is. So one of the telltales about this element is its density. So you measure the density of the object in the lab, and you go and compare it to standard, basically, densities of other materials, okay? And depending on what you find, depending basically on the number, you will see a match. Oh, you say, that's really what this element is. Sometimes you need other confirmations, though, using other processes. But the point in here is density is related to a specific compound, a specific element, or a specific object. So that's really what the density is. The definition of the density, again, is mass over volume. You double the mass, the volume doubles all the same time. So if you multiply this by 2, also this one goes by 2, this number doesn't change. The density is a property of an object. So another number that's probably worth remembering is the density of water, also in terms of grams, is 1 gram per cubic centimeter. That's also another unit for the density, okay? So again, the water here is usually as a reference, okay? So that's a good thing in here that we can look at these things in here and compare them to water. So this is, for example, mercury. Again, mercury is, which is a kind of, at the room temperature, sometimes it's a liquid, but that's not, it's actually a metal, okay? But these are some of the properties of some of the materials. Any questions so far? Okay, the standard unit for the density is actually kilogram per cubic meter. But you will find that this number is big usually. For example, for mercury, it's going to be 13,600 kilograms per cubic meter. That's a big number. So instead of that, people use the gram per cubic centimeter, but because it's 13.6 is better than 13,600,000 kilograms per cubic meter. That's a big number, okay? So 13,000, not 13 million, I'm sorry, 13,600 kilograms per cubic meter. So that's a big number, because a cubic meter is a big thing. Think of it I'm trying to basically move away in here to show you how a meter is. So it's from end to end to between my hands in here. That's a meter. Think of this meter, and you move it away one side, and you move it to the other side, and that is what a cubic meter is. So it's a lot of volume. It's a lot of space. So if you think of that and put water in it, that's going to weigh like a car, like an average car, basically. So you put that, fill it with water. That's why it's a ton. That's why this number is big. So if you can have that volume, and it's a big volume, because if you open your arms, that's about a meter, or open your basically step with with your feet. So that's about a meter, okay? So that one, and then think of it this way, and we are barely above a meter. We usually were around 1.5 meters to 2 meters on average, people are. So think of it as about 2/3 of your height, or a little bit more or less, depending on how you are. That is the space that we're talking about. That's a cubic meter. If you fill that with mercury, of course, it's going to weigh a lot, because it's a lot of weight in here. Okay. That's because mercury is super heavy in here compared to, for example, liquid water. If you fill it with water, it weighs like a car. And this one weighs a lot more, like, what, 13 cars or 12 cars or 10 cars, depending on the make and the model, okay? So that's the concept of density. Again, the density is specific to an element itself. I'm trying to give you a visualization. If we were in the classroom, we would actually take a tape and measure it and see, and from there on, you will have a visual in your head, because if you don't see these things, it becomes like science fiction. Basically, anything is out there and it doesn't connect. But if you have a visual of how this looks like in real life, what a cubic meter is, then it makes sense, especially when you compare it to something tangible that we deal with on a day-to-day, like a car, for example. So that's really how you can think of it. Take a car, compress it to about a cubic meter. Cars are they're less dense than water, because of the fact that they have a lot of space inside of them, and they become what we're talking about. Okay, in addition to in the United States, basically in here, they use the pound a lot, and you can use the weight density instead, which is pound per cubic feet in this case. But again, that's only specific to here. Okay, so water, what is it? More dense than fresh water. So the density of the fresh water. Look at this number in here. Which one? And be honest, okay. Which number can you remember easily? 62.4 pounds per cubic feet, or 1 kilogram per liter. I mean, the word kilogram and liter may sound foreign, and but the number 1 versus 62.4. I will take 1 any time of the day, okay? I'll remember much easier that number than 62.4. Unless somebody is willing to bet otherwise. Which one is easier? 62.4? Remember? Okay. So I'm glad that people agree, okay? So it's easier to remember that than the 62.4 pound per cubic feet. I mean, sounds foreign to you guys, but for me, actually, the pound and the feet took a long time for me to adjust to, and I still struggle with them, honestly. I do conversion all the time. Okay, sometimes fast, but I try to convert them to have, again, that visual I was talking about. If the weatherman tells you the temperature today is going to be 73 degrees and it's beautiful, for somebody who was raised in a different kind of temperature, 70, are you nonsense? That's not right at all. And then you do the math. Oh, that's good. 73 is good. So that's, again, because the numbers, they say things, they talk to you. If somebody tells you the temperature tomorrow is going to be 117 degrees, you know exactly the type of clothes you're going to wear, you know exactly the attitude you're going to do, you know exactly probably what to do, and you're already planning to be somewhere in a specific place to cool down. If somebody tells you the temperature is going to be tomorrow 27 degrees, on the other hand, you know exactly also you have a different attitude and preparations for it, because numbers talk to you, tell you things. That's why it's a good idea to remember them. So again, which of this has the greatest density? 100 kilograms of lead, 100 kilograms of water, both are the same or none of the above. These numbers don't mean anything. Again, 100 kilograms of lead or 1 kilogram of lead or 1 gram of lead, they have the same density. Because again, the density has nothing to do with the amount of matter. It's basically a ratio of two things that increase or decrease proportionally if they are pure stuff. So the correct answer for you guys is lead. Lead is actually more dense than water. Okay, the density of water lead is about 8 times or something like that than water. So it's denser. So the number 100 kilograms doesn't mean a thing in this case. Okay, this is the other concept that we will need, like I said, is the force divided by area. If you have 1,000 kilograms of water and you spread it through a thin area, spread it thinly through a big area, it's going to exert less pressure than it does if you spread it, for example, the same ton of water, you spread it, for example, on a smaller area. It will have more effect, far more ways that way. You can think of this, for example, sharp object in here. I have a small screwdriver in here, and if you have a sharp end versus a wide end, with the same force is going to exert more effect. So what you feel in this case is not the force, you're feeling the pressure. That's why the pressure matters in here, which is the ratio of force over area. Again, it depends. So the standard unit for force for a pressure is actually Newton per meter squared in the standard system of units. But we got sick and tired of calling it Newton per meter squared, Newton per meter squared, and in honor of Mr. Pascal, basically in what he did for in this area, we are calling it Pascal, PA. Okay, so this is the standard unit for pressure. I know that you use pound per square feet, and that's something else that is used probably, especially here if you call somebody to come and work on the pipes or something like that, and he wants to work on it, and he goes to Home Depot, he will not find things in Newton per meter squared, probably maybe hidden right in the label there is that, but up front he will find this number. Okay, so that's why we'll use pound also per square feet. Okay. So in the liquids in general, the pressure depends on the depth. That's basically what we can argue, and there is a reason for it. Is, for example, if I take a column of this fluid, okay, we can argue that the pressure on both sides on each level is the same, but the pressure differs from one side to the top and one side from the bottom. And if you think of this column of fluid is made up of actually fluid, because it's not empty. The fluid has fluid in it everywhere. But again, if I throw my coloring fluid, for example, in the fluid, is going to stay in its place. So this column is going nowhere. It's not going up or down. Granted, it's the same fluid. Okay, it's not a real, not a real column of a different fluid, or even the fluid itself. It's not. It's a mathematical, if you wish, fluid. But this object is under its own weight. That's one thing. So if there was no difference in pressure, this column of air, this column of fluid should sink to the bottom, should fall under the F equals to ma again. F equals to ma dictate that since there is an external force which is due to gravity, so it's going to sink it. So the only way this column is not sinking, if you can think of it this way, that there is a force exerted by the fluid on it from the bottom, and of course from the top probably, that keeps it in place. But the imbalance in these two forces will equate the weight. That's why there is more pressure in the bottom than the pressure in the bottom and the top. So, which means that the depth dependent only, that's how the pressure is, depends on how deep you are. The closer you are from the top, the less pressure the fluid exerts. The lower, the further you are from the top, the more pressure it exerts. So that's basically how the mathematical proof for it goes this way. And actually we will see down the road that this pressure actually is equal to the weight of the water times the depth. So if they are just on the below the depth, below basically the surface of the water, you're not going to see any much pressure from the water. But if you move further and further and further down, you're going to see the weight of that water added more and more to your body, and you will feel the pressure up to 10. That is in addition to the atmospheric pressure we're going to talk about. So that's going to be about at about 10 meters. You're going to feel another atmospheric pressure And if you go deeper and deeper, you're going to feel more and more pressure. If you don't have proper equipment, actually, you're going to implode because of that pressure. I mean, your outside will go inside, and it's not a pretty picture. So basically, wear something, okay? Wear protective gears if you're going to do that deep in water. I mean, a swimming pool, probably what? It's 4 meters, maybe 3 meters. So you're not going to feel much difference. I mean, you're not probably going to feel it as much as if you go, for example, under, if you're going to go, for example, in a lake or something like that, in a swim underwater. So you really have to have protective gears, okay? Swim as deep, and the pressure due to the weight of the water above you is twice as much. Does this make sense? Yes?
Yes.
Yes.
Very good. So again, the pressure is normal to the entire surface. It's coming from everywhere on the body itself. So it's not just coming from the top and the bottom, it's coming even from the sides. But the sides cancel actually, because the same pressure is coming, because we're at the same level now on the sides. Basically, we're at the same depth from the side. So the pressure on one side, the pressure on the other side. But of course, it doesn't mean that you're not going to be impacted by it. I mean, if two people pull you from each side, yes, their forces cancel, it's true, but what happened to your arms if they keep on pulling? Yes, so it's not completely, so you have to have strong, basically, connections in here, or you're going to lose your arm. Same thing with your pressure. I mean, yes, they cancel because this pressure is equal, I mean, the force coming from this pressure and the force coming from the other pressure, they're the same forces. So Mr. Newton's law perfectly says you're not going to go anywhere. F equals to ma, and F cancels, the sum of the forces equal to 0. So you're not moving according to the first law, at least on sidewise. But if these forces continue to increase, you better have protective gears in here. Otherwise, you're going to give in yourself, and that's not good. Okay? Again, it depends on how high you are. That's why there is less pressure in here than, for example, this one. And the fluid as it exists from here exists at a higher velocity. So this is like a projectile, like you throw a rock. So you throw a rock with a smaller velocity and it's going to land not too far. You throw it with a higher velocity and it's going to have a higher range. So again, that's the projectile motion. So think of each particle of the fluid as it's coming out as a projectile, one of them with less initial velocity than the one in the bottom because of tremendous pressure coming from the above of the fluid. So that's really how we do this experiment actually at some point, but unfortunately we're not in class to show that. And you will see actually the water flows falling in a specific point from one cup, and the other cup falls further depending on where you puncture the cup, basically. Puncture it, put your finger on it, puncture the other one, mark where the place is, and it's a very easy experiment to do actually. So acts equally in all directions, that's the pressure. And again, which way you change your ears, it's not going to matter much if we're talking about underwater. We have a lot of slides and we're on slide 12 and we still have very little time. So probably, again, this I talked about already. The pressure depends on the depth times the weight. What did I say in there? Did I say the weight? That's wrong. That's the weight density. Okay, that's the density. The weight density is really the density of the fluid, which is usually written as, let me write, the density times the gravity, not the weight. That's wrong, okay? It's not the actual weight. It is the density, weight, which is mass of the fluid times the gravity, the force of gravity. But this is not the actual, how should I call it? The actual mass, but the density of the object, or the density of the fluid, I should say. So the density of the fluid, let me write this expression in here probably. The density of the fluid, not the density of the object being submerged, okay? Times gravity G, which is our 9.8 that Mr. Galileo has computed for us, times the depth. Okay, that is going to be pressure. That is the pressure. Okay, again, you will have some assignments and some of them will require numbers. So probably you will need to remember these things. Okay, so if we tell you the water density is 1 kilogram per liter or 1,000 kilograms per cubic meter, and the object is, for example, at 5 meters below. So you multiply 5 times 9.8 or 10, if you like, times 1,000. 1,000 times 10, that's 10,000 times 5, that's 50,000 newtons per meter squared, or 50,000 pascals, if you like. So that's simple. You're not required to remember all of the steps, but down the road, if there is an assignment, we're going to talk about this one. But just
Quick
an
question
idea.
for you, Professor.
Yes. Yes.
So what you have circled in the middle of this PowerPoint,
Yes.
that is the correct, or it is
Yes.
not?
That is the correct expression. Yes.
Okay.
When I wrote it earlier, I said something in here W, and that is wrong. That is not correct. Okay. It's
Okay.
the density of the fluid times G.
Yeah.
That is what the weight density means, really. Okay. The weight density is the actual density times G times, remember that G, 9.8 that Mr. Galileo has measured for us. Okay.
Yep.
Okay, so the force of gravity acting on the tower, that is why they have usually the towers up high in the cities, so that they use gravity to basically bring the fluid down to the water faucet. Which brings us to a question that is of the day today, so that you guys remember to answer it. Okay, this is not the answer to the question, okay? So the answer to the question is something else. It's not D, okay? So so remember, this question is going to be after the session today. We're going to go to a discussion, and you're supposed to answer not necessarily the only question, though, but you may have one or more questions down the road. But if not, that's the only question you will have. Suppose water from a tall tower supplies a nearby home. If water faucets upstairs and downstairs are turned fully on, both of them are on, will more water per second flow from the downstairs or the upstairs faucet, or will water flow the same speed? Think of this scenario. I can't find it again. Where is the picture? Here. You have a water in the top and water in the bottom. Which one will have more fluid flowing over it? The one in the upstairs or downstairs, or the same? Any question, takers? I know you have the PowerPoints. So the correct answer is downstairs again, because if it's coming from the same source and both of them are coming to the faucets and using just the gravity in this case, there is no pump, for example, in the upper stairs, so to pump more fluid to it. There is no mechanical pump whatsoever. Then in this case, hey, the water downstairs will have a higher flow of liquid. So the correct answer is either A or downstairs. Yes? Okay, very good. Everybody is on board right now. So the correct answer, either A, or if you wish, downstairs. That's one of the questions, okay, that you might have today. I mean, that you definitely will have today, but this, in other words, you might end up with more, okay, depending on how fast we go. So the correct answer is A. And this is one of the tricky questions that you guys probably need to remember also. Does a 3-meter deep lake, this is a lake, okay? I don't know what's the lake, what's the biggest lake? What is near Norco? Any idea? The Salton Lake is very far, okay?
Natural or man-made?
It doesn't matter, any big lake. Any lake, somebody answered that already? Let me stop sharing. Oh, no, what I want to know is, Masada, if you tell me if you know any big lake in here, near where we are.
I don't think Lake Paris is very big, but it's a lake.
It doesn't matter, it's a lake. Lake Paris is the closest. Yeah, I was not too far from it on the weekend. Anyway, so Lake Paris versus a small pond, okay? Small pond, not a big one, too. One of them is 3 meter. The lake is being 3 meter deep, whereas the other one is a 6 meter deep. So in this case, it doesn't matter the amount of fluid you have. It's the depth that matters only. So yes, Masada and everybody else, the correct answer is B, the pond, albeit it has less fluid in it. It's, in this case, so this is not one of the questions that you're going to be doing in there, okay, in the bottom. Okay? And one of you at least did what he or she did, was answered all of the PowerPoint questions in the after question in the discussion. Okay, you don't need to do that. Basically, let's just keep it. But by the way, the other thing also that we need for those after sessions is if you have questions related to the topic, please don't ask them in the sending them as messages to me. It's a good idea to ask them. That way you might end up with probably a better question, or you might have a different insight to the same question that benefits other people. So please do ask those questions or comments, put them in there, put them in the after class basically sessions. That is what I'm trying to instill in you guys in these things. That's why I'm trying to do these things more and more. Down the road, as we move along in this course and toward the second half of it, we'll do less of these things. The intent of it is to have you fully engaged with one another and with the course content and with me, so that we have all of these things communicated. So that's what I'm trying to really build with these things, and that's why we're actually being compensated for it, getting grades for it too. Okay, so this brings us to the buoyancy, which is another concept in here. And that is the apparent loss of submerged weight of submerged objects. Basically, you put an object in the liquid, and you feel lighter. The object feels lighter. As a matter of fact, you weigh it, and it's going to weigh less than its own weight while it's not in the fluid itself. Okay, and the force that is exerted by the fluid on the object is equal to the displaced fluid. So this observation was supposed to have been made by Archimedes, who basically came out of his tub completely basically in his natural clothes, yelling "Eureka, Eureka, Eureka," namely that I found it, I found it, I found it. And that is Archimedes' principle. Okay, that's from that point on it was called after him. So discovered by Greek scientist Archimedes, relates buoyancy to displaced fluid. So he explained that this force that we feel is actually equal to the weight of the liquid that is basically displaced, and states that an immersed body completely or partially is buoyed by a force. That means that it's lifted by a force equal to the weight of the fluid it displaces. And this is true for both liquids and gases. Okay. Again, this is the experiment that if we're in the lab, we'll do this one too. Basically, you take an empty bucket in here, and you take a container that is filled to the brim, filled to the top. Okay. And you submerge an object in it, of course, because it's filled, then in this case, the object will displace fluid. And if you contain all of the fluid in another container, and weigh this object in the same time, this object has a certain weight. For example, in the example in here, it starts with 3 kilograms. But if you weigh it now while it's submerged, it drops to 2 kilograms. The reading on the needle was 3. Now, I'm sorry, it drops to 1 kilogram. So the reading on the needle now is 1 kilogram. So you ask, what happened to the extra 2 kilograms? Where did its weight go? It feels lighter. It required 3 kilograms to lift it. Now it's only 1 kilogram of force, which is 10 newtons basically to lift it instead of 30 newtons to lift it. Then in this case, what happened? You weigh the liquid that actually has escaped, and you will find that that's actually weighs 2 kilograms or 20 newtons, that is. So that's where the formula is coming from. So this is an exact match for this one. It's a simple enough experiment that we do also in the lab, especially for classes like this one, general physics, where it's very easy to see what happened in this case. And it's a deep concept, okay, because it explains a lot of things. For example, the condition of flotation, for example. When can an object float and another object doesn't? Because there's a lot of engineering going in there. So if you're going to build a boat or canoe, you have to be careful. In the canoe, probably that you build out of wood, it's not going to be an issue. But the one that you build out of metal is going to be an issue, because metals has a higher density than the liquid, so it's supposed to sink. But if you have a proper geometry for it, it's not going to have a problem. So again, this is the completely submerged object displaces a volume equal to its own weight. How big is the volume it displaces? It's its own volume, its own physical size. Okay? It has to be the physical size. No matter how much it weighs, no matter how much its density is. So buoyant force is equal. So the further the object is, it's the difference in pressure also. You can explain it too in this term. So if I have twice pressure, for example, as in the top, so the difference between them is one value of pressure. So if now quadruple the value in this case, multiplied by 4, this one only triples because I need to retain that difference of one value, one numerical value. So it doesn't go proportional now. All of a sudden, the object is squeezed from the top or something, or relaxed or something. Same thing. Now, if I go 6 times, this one goes 5 times to retain that difference of 1. So it's just a difference in pressure. That's basically where the buoyant force is coming from. Of course, since it's a force, I have to multiply it by an area in here because the area matters now. Since I'm looking for the force in Newton. Remember, the pressure is force over an area. So if I want to get the value back in terms of Newton, I have to multiply it by the area that this pressure is applied on. So buoyant force is equal to the weight of fluid displaced, the weight, which is in newtons. Okay. Here's a question for you. Which of these blocks submerged in water is a buoyant force greater? Is it 1 kilogram of lead, 1 kilogram of aluminum, 1 kilogram of uranium? And in this case, the 1 kilogram matters. Okay, the amount of stuff matters. But what matters also in this case also is the density. Lead is denser than aluminum, which is less dense, and uranium also is denser. That means if I bring 1 kilogram of lead, it has smaller volume than that of an aluminum. If I bring 1 kilogram of uranium, it has less volume than aluminum. The aluminum has the biggest volume of the 3 in this case because it has less density. So this is less dense, means it's bigger volume for the same amount of stuff. For the same 1 kilogram, I will have more aluminum than more volume of aluminum than volume of lead or volume of uranium. In this case, it's going to displace more water because it has bigger space. It's going to move more water when it's going to sink in. So in this case, it should the water should exert the greater force of the 3. So the correct answer should be for aluminum. Does this make sense to you guys? See the argument in here? It's multifold argument. The first one is you bring the density into the picture and see which one is the denser of all of the objects, or the least dense of all of the objects. The least dense of all of the objects for the same amount of mass should occupy more volume. Since it's going to displace water, it's going to displace more water. So that's a multi-argument statement to arrive to the conclusion that it's actually aluminum in this case and not the others. Yes? Good. So again, this is the principle of flotation. Again, we're bringing the same amount of iron in this case in the picture, but one of them is configured in such a way that it looks from the outset that it has less density than the one from the other. Both of them have the same density. Both of them are iron. Both of them should sink if they're in a smaller block. This one will displace less. This one will displace less water than the other one. This one displaces more water. Therefore, the buoyant force in this case will equal at least or more than the weight, so the object will float. This object in here will displace less force, so there is less buoyant force in this case, and the weight will win in this case, so it's going to sink. Okay, so the shape in here matters because the 1 ton of iron is still the 1 ton of iron, but when you spread it throughout a bigger surface, in this case, bigger volume, then in this case, it looks like you're displacing, it's actually not, it looks like you are displacing more liquid, in which case you increase the buoyant force. But if you put them in a lump sum like this one, iron will sink. That's why you can engineer a lot of basically boats that are made out of iron, travel the seas and take goods from country to country. This is a question that has to do with the person finds it easier to float in salt water compared with fresh water. Is that because the density of the salt water is higher than the density of the fresh water, and now you're going to move less of the other one than the first one. So that's why a smaller volume of water is displaced because it's less dense than the first one. It's the same person, same weight. Okay. Okay. On a boat ride, the skipper gives you a life preserver filled with lead pellets. When he sees the skeptical look on your face, he says that you will experience a greater buoyant force if you fall aboard than your friends who have styrofoam filled preservers. So is he right? The answer to this question, yes, because you're taking lead with you, and lead is denser. So in this case, it's going to basically the same amount, the same preserved, filled with the same. So it's going, because it's more, so it's going to displace more liquid. So you're going to basically, in this case, exert, at least be subject to a higher buoyant force. But of course, because of the density, it's going to sink. So yes, he's correct, but don't take his pill. That's really actually he's trying to get rid of you. Okay. Okay, that I think okay, we need to move on. We have about a little less than half an hour, actually. Unless you guys have any questions about the liquids, now we're moving to gases. Gas pressure is a measure of the amount of the area that exerts against the containing wall. Again, if you do the theory for this one, and there is a kind of sad story that I always try to remember when I come to this point in here, because we were trying to understand Gass's law, and there were a lot of people working on it in the 17th century, toward the end of the 17th century and the 18th century, actually. And actually to the 19th century, toward the end of it, Mr. Boltzmann came up with a theory basically explaining the gases, basically the pressure in the gases. And he said, look, gases are made up of tiny particles. Nowadays, we call them molecules, basically. And those tiny particles, they hit the wall, and he came up with a beautiful mathematical explanation based on Newton's laws of motion. But of course, peer pressure sometimes plays a role, including from his peers, scientists, basically, and people who are making fun of him. Hey, Mr. Boltzmann, I'm going to grab some of those imaginary particles that make up the gas. Here they are. Can you hold them? And there was too much pressure on him. He committed suicide at the end. The point being in here is, afterwards, of course, it turns out he was right. I mean, Boltzmann theory is perfect and explains all the gases laws, basically, the classical gases laws. So he was completely 100% right. And sometimes pressure sometimes plays a bad role on people. And we have this, the bias and things like that in science that we're not supposed to have, but sometimes it comes in and plays a negative role. He was a genius, of course, and his explanation until now, Boltzmann theory is still perfect and explains a lot of things with gases and things like that. So that's something that is, nowadays we take it for granted because we know molecules exist, and that's what makes, for example, the air molecules are made up mainly of nitrogen gas and also oxygen gas. So those are the two main components of the air, and that's basically how I can explain, at least for the air, other gases also experience similar behavior. But again, as on a cold day, the molecules are moving and hitting the wall and hitting your skin, and you feel them. But they're moving slower than on a hot day, for example, like yesterday and the day before, where the molecules are moving very fast and hitting you. And once they hit you, in this case, hit your skin, then in this case, they impart part of their kinetic energy to your skin, and that's what you feel as temperature. That's what you feel as heat, actually. So that's basically how this concept is, and it works beautifully in this theory, okay? Again, the density in here, well, there is some good news, some bad news when your tire goes flat. The good news is, and I know you say that the tire is flat, it has no pressure. Actually, it has pressure. So the good news is, it still has pressure, and that is because of the atmospheric pressure. But the bad news, of course, it does not have additional pressure to that. Otherwise, the tire is flat and is not going to move. So again, in this case, it's related to the density of the gas inside, okay? And what we read in here on the gauge, which is called the gauge pressure is in addition to the atmospheric pressure, okay? And again, more dense gas, more pressure. Less dense gas, less pressure. Another way of thinking about it, to build more pressure or more density, is actually change the volume. Shrink the volume, then in this case, there is more material in less volume, so it's a higher density, so which means it's higher pressure, so the gauge pressure will be higher in this case. Okay, just bring the piston down. Which brings us to Boyle's law. Boyle's law and Charles, and there's another one in there. So they all actually can be explained with another law that we know nowadays, and you probably had it in chemistry, or you will have it in chemistry, or probably heard of it. And if you did not heard of it, this is another thing to remember. So if you're running out of space in your head, remove one of them, like for example, your birthday or something like that. This is another law. nRT. This summarizes everything, the one that we're talking about. Pressure times volume is equal to the number of moles times a constant in here, which is R, times the temperature, and the temperature is another concept that we will need actually for gases. We didn't mention it, and we briefly talked about it when we were in this slide, okay? That's what you feel as temperature actually, okay? So that's a great law, but you don't have, you're not accountable for it, this one, at least up to this point. This is a summary of that. So if in the case the temperature is the same, the gas is the same, the pressure on one side times the volume on one side does not change as long as you don't change the temperature, the gas temperature doesn't change, and of course the gas doesn't change at all. You're not going to inject more of the gas or extract more of the gas than this pressure when you change it. So take a balloon, for example, and squeeze it. In this case, it's in contact with the air, so the temperature doesn't change. So the new volume now is more volume, but there is more pressure now. So if you squeeze it to half its own size, it's going to have twice as much pressure. So if the volume drops by a factor of 2, the pressure has to increase by 2 so that the 2 and the 2 cancel, and the number stays constant. So that's basically what this is. Okay. Which is exactly the point in here. When you squeeze a party balloon to 0.8 its volume, the pressure must increase by 1.525. So that's 1.05 times 0.8. That should be the same as 1. So it doesn't change, okay? 1.25, not 1.28, okay? So if you multiply it by 0.8, it should be exactly 1. It does not change. It's a good idea to check these things, okay? Don't never take my word for things, okay? Because sometimes I make mistakes. Not sometimes, a lot of times actually. Okay?
You should have brought a balloon with you today. You could have tried it.
Yeah, I have some at least in here. I have a lot of junk in here, but sometimes I don't basically have chance to go through them. And
or maybe make some like animal balloons for us.
believe me, if we are in class, we have a lot of equipment in there that we can pull and basically do stuff with it, and it's fun. Okay. Unfortunately, we're in COVID times, so take my word for things. Okay. If not, try it on your own. Okay. The Magdeburg also, I had one, but I don't know what it. I think it's in the garage somewhere. Okay. Again, that's the demonstration for the air pressure. Okay. You put pressure, you remove the pressure from it, and now the air pressure will not be. You will have a lot of force trying to impact to open it. So what is the air pressure? It's the weight basically of the volume of the air that is on top of you. You're sitting now, or you're standing, or you're sleeping. It doesn't matter what situation you are in right now. You are under atmospheric pressure. You are carrying with you 100,000 newtons per meter squared. That's how much you're carrying. So don't tell me you can carry a car, because a car is less than that. Okay, this is, think about it, this is 10,000 kilograms per cubic meter, per meter squared, I'm sorry. 10,000 kilograms. That's a lot of weight that you're carrying. About what, 10 cars right now as you're speaking per meter squared. So that's a lot of weight. That's basically how we're accustomed to it. That way, if we happen to land tomorrow on Mars, we'll have a problem. Without protective gears, we're going to explode, because the atmospheric pressure on Mars is very, very light compared to the atmospheric pressure on Earth. So our bodies are accustomed to this much pressure, so we're going to explode. If we land tomorrow on Venus, on the other hand, the atmospheric pressure on Venus on the surface, granted we survive the heat and all of that nonsense, and Venus, the pressure itself will make you implode, because it's about almost 10 times higher than in here on Earth. So again, there is tremendous pressure on the surface of Venus versus that on the Earth. There is a lot less pressure on Mars than that of the Earth. the only safe place in terms of the pressure for the entire system, solar system, other than the Earth, is actually one of the moons of Saturn. What is it, Titan? So that's the only moon where the atmospheric pressure is comparable. It's slightly higher than that of the Earth, and that's the only one that probably we can stay comfortably in there. Granted, we have masks because there is no oxygen on the surface of Titan because it's made mainly out of nitrogen. Okay, which is really what our atmosphere is also. It's mainly nitrogen too. So it's a similar atmosphere, except we have more oxygen in here than on Titan. Okay. Again, so the pressure exerted against bodies in immersed. So this is the other number that's worth remembering. And I already throw it in there, 100,000 newtons per meter squared, or 100,000 pascals. And 101, to be more specific, kilopascals. To be more accurate, it's 101.3 kilopascals. Okay, 101,000 pascals. That's the number that the atmospheric pressure that we're all sitting under right now, and we're subject to wherever we move in the Earth in here. The weatherman talks about slight modifications. So when he says that the pressure is rising or the pressure is falling, it's a small fraction from this 100,000. So usually it's millimeters or whatever that is of the mercury. So it's very small variations. So with the small variations, that brings a lot of wind. And right now we're subject to the Santa Ana wind coming from the inside, basically inside the country, going toward the oceans. And when we have it backward, it's actually better. Okay. So again, that is because of the difference in pressure in the atmosphere. But the atmosphere itself, since it's around 101,000 on average, goes slightly more or less, and that makes a big difference in terms of weather. If you were to use just the atmospheric pressure to pump water from a well, for example, the maximum you can do is to pump off of it is 10.3 meters, because below that depth, the atmospheric pressure will be less than the pressure from the liquid. So basically, if this is, for example, the depth of a liquid, for example, or for example, the ocean, the minute you reach 10 meters, you will be subject to an additional atmospheric pressure than the atmosphere itself, and that is coming from the water. You go another 10 meters, you will be twice the atmospheric pressure plus the atmospheric pressure. You go 100 meters, at that point, you're looking at 10 times the atmospheric pressure. Your body cannot sustain it. 10 times is too much. Your body actually will implode in this case. And that is only 100 meters. You go 1,000 meters, and that's going to be even higher. Okay, it's going to be 100 times the atmospheric pressure. You go about the bigger depths are about 10 kilometers. So in that case, the atmospheric pressure will be 1,000 times greater under the oceans than that is of the Earth, and you cannot survive that much pressure. Which brings me to an important question, and this is another question for the day that you need to answer, and it's not in the slide, so you're not going to see that question there. How does the fish do it? Why does the fish survive at a depth that are about 10,000 meters, about 10 kilometers in the ocean than we do? Why? Is the fish stronger than us? Does it have armored chute that we don't have? Any takers? So again, for those who are probably so this is the other question for the day. Does the fish survive deep water depth, such as, for example, 10 kilometers? Any idea? Doesn't matter, okay, guys. Their bodies are more durable. Have you held the fish, Rudy? Is it more durable than us? Body functions. What do you mean, Sarah? That's the correct answer, by the way, but it's not.
Just anything having to do with the way that they were created.
It has got to be something to do with their lungs and their gills.
I think you're almost there. Like Joshua has answered the question, okay? Do you guys see it? That is the answer. Yes? Their ability to breathe air. No, their ability to breathe the water. Because they cancel the pressure from inside and out. I mean, there is tremendous pressure. And that's why they don't implode, because the pressure inside the fish is the same pressure outside. So for them, it's no big deal. Same thing for us in here, we're not a big deal. So here is the secret for you if you want to survive that many depths. Breathe the water. Yes? If you want to survive any depth.
That's a little difficult as a human.
So that's the answer to today's question. Okay, Sarah. Okay, that's the answer to today's question. The only reason why the fish survive in this much depth, or the reason why fish survive in this much depth, is because they breathe the water. That's why. That's the answer to. This is the second question of the day, and again, it's not in the slides there. Okay. Okay. Again, we're going to talk about, with a mechanical pump, of course, this is one of the things, one of the questions about the straws. How much can you drink off of a well, for example? The maximum depth you can drink off of a well with a straw is 10 meters, 10.3 meters to be more specific. If the water depth is 10.4 meters, for example, and you try to drink from it, you cannot empty enough air, because the biggest column in there is equivalent to 10.3 to drink from that water. You need a pump. Okay, and this is a mechanical pump. For example, there is this thing which is spinning. When the piston is up, it's going to intake the water in. Then when it's going in the second cycle, which is going down, it closes the intake and opens the outlet, so the water is going to be pushed one way or the other. Okay, so this is a mechanical pump, the principle behind it. And we still have less than 10 minutes, and we really need to finish this thing. Oh, no, I'm sorry. We still have more. I thought it's done. No, we still have more, but we have to really finish it as quick as possible. So the barometer is a measurement of the pressure, and also because the higher you go, the less pressure. So it's actually a measure also of altitude. So it's called, sometimes when it's calibrated for height, it's going to be called an altimeter. Okay. Question, atmospheric pressure is called why? The density of Earth atmosphere, no. The weight of the Earth atmosphere, no. The temperature, yeah, the weight of the atmosphere above you. That's how much it is. The weight divided by the area. So that's what the atmospheric pressure. Again, this is another question for the day. Okay, and that is that two people are drinking soda using straws. Do they suck the same soda? They suck up the same soda? The question is no, depending on how much each and every one of them opens, basically, pushes from the air, basically. Could they think of a drink of soda this way on the moon? Of course not, because there is no atmospheric pressure on the moon. So the correct answer is C. So those are the three questions for the day today. The first question was, I think, what is it? A, the answer to it. The second question, because the fish breathes water. And the third question is this one, okay? No, they cannot drink. They don't have necessarily to drink the same amount of soda, although they are drinking next to one another. And no, they cannot drink on the moon because there is no atmospheric pressure on the moon. There is no atmosphere on the moon. Okay, Pascal's principle, and this is really what leads to the so-called hydraulic press. And this is sometimes referred to as U-tube. Actually, this was well known before what you guys know as today's YouTube, okay? This is what we call U-tube in physics, and this is the one that is usually actually to measure the relative pressures and used also in the principle of hydraulic press. This is, for example, what is used in mechanical shops to lift engines and to lift cars and things like that. And they use very small. So the principle behind it is that the pressure will distribute equally in an equal volume, basically. So if you exert this much pressure in here, P, let's say, for example, 10 Newton per meter squared, the 10 Newton per meter squared will spread itself and find itself on the other side. Now, because the pressure is related to the force, then this can be converted into a simple machine, which is exactly what it is. In a sense, a 10 kilogram will displace, will exert the same amount of pressure and can be moving this much basically liquid for the same amount. And then in this case, it's going to move the 500 kilograms, albeit with less distance. Okay, remember the principle of simple machines, they cannot generate energy. The energy is the same on both sides. So a 10 kilogram piston, what is it? So the same pressure, remember the pressure on this one is 10 kilogram times 10 meter per second squared. That's 100 newtons. 100 newtons, my pen is not, okay. 100 newtons divided by whatever area in here is, area 1 is equal to 500 times 10, that's 5,000 newtons, divided by another area. But this area is bigger, so the ratio stays the same. So you can lift the 500 newton, okay? So both sides will have the same pressure. That's Pascal's principle. Okay, and this is the formula I just used. The pressure on both sides is the same, and this is the ratio of the forces. This force is called the effort. This is called the load. Okay, F2 in this case is the effort. F1 is the load. Okay, F1 can be greater than F2, granted that the area A2 can be greater than the area A1, and they are the same number. Okay. But the work in this case of this force is this force times this displacement, and the work in this force is this force times the displacement, so the displacement will be less. In other words, you're going to, yes, achieve it, but not with the same height, because you cannot make energy out of it. And this is what I was talking about, the hydraulic press used to lift engines in this case. What is not possible in this situation, the correct answer to this one is energy output exceeds the energy input. Yes, you can have moved the pistons at different rates. The forces can be different. The output, of course, the speeds can be different. All of them have to do with power and energy. But the thing with it is the energy of the output cannot exceed the input, because no matter how big you are, you're not going to make energy out of nothing. So the correct answer is D in this case. The buoyancy, again, works the similar way. I was driving actually on Highway 215 over the weekend near Hammett, and I saw so many balloons in there. And they displace how much liquid they displace, which is the air in this case, how much air they displace. And the net force, again, is going to be equal to difference in pressures, and that is exactly what the buoyancy is. So that's how you lift off. There is no engine in there. We need to get into Bernoulli's principle very quickly, which brings me to the fluid flow. And this is basically what we can think of as an imaginary streamlines. They are not real, okay? So this is basically where the fluid flows from one area to the section. If I count this volume of fluid, for example, that traverses this section of the fluid, it's the same volume of this fluid that traverses the same one. So the volume in this case is the velocity times the amount of time times the cross section. That is the volume that traverses times, and this is the velocity in here. Therefore, because it's a small area, this fluid will move faster than this fluid. That's why when you squeeze the ends of, for example, of a tube, the fluid will come out further depending on how much you let go. Okay, if you let small amount, it's going to travel further away. That is what firefighters do sometimes to fight fires with it. So the principle of Bernoulli in this case is basically the speed of a flow increases and the internal of the pressure decreases. Okay, actually there is another parameter that is actually included in Bernoulli's principle, and that is the fact that depends on the height. But if the object is small, for example, then in this case the height doesn't play a major role. Take, for example, the case of a curved ball or a ball that is spinning, for example, in baseball. If it's spinning this way, for example, down, so this side of the fluid is this side of the ball is moving in this direction. The entire ball is moving in one direction. The entire ball is moving this way. But this side is moving forward while this side is moving backward. So it appears that this side is moving slower because the resultant of these two velocities than this side. For example, if you are a person living on a baseball, you appear to be moving further in this case. You will feel the rush of the air higher on this side than in this side because part of it is going to flow backward in here. Because this velocity is higher, so it exerts less pressure than the velocity, less pressure than this side of the baseball. So this pressure P1 and this pressure P2, or the in the bottom is higher than the pressure in the top. So it's going to experience now a net force which is going to rise it. And that's why the curved ball sometimes will basically appear to move on the batter when he's trying to switch. And that's why curved balls sometimes are very hard to hit, because of this motion, because of the difference in pressure in this case. If it's spinning backwards, it's going to fall in the opposite direction. Again, where the speed of the fluid increases, the internal pressure decreases, so the pressure in this case is, actually, I'm sorry. Yeah, that's correct. P2 is higher than P1, it's going to rise in this case. And again, you can do it sideways too. You don't have to do it. So this is basically, in a sense, how the baseball works. And actually, this is also the principle of how wings, how planes actually take off. Let me go to the slide, for example, for the wing, because it's an important concept in this case. This part of the air that left is going to meet this part of the same air. So think of this two streamlines, for example. They left, they greeted one another, we'll see you later, and they meet again in the same time in the same place. Because from far away from the wings, sides on the air looks calm. So whatever air is in here is in the air in there. So as the wing is rushing through the air in this case, the fluid appears to be moving at different rates. So for this one to go around the curve and come back and greet its friend, the one that is going on a shorter distance, this one must travel at a higher distance than the one in the bottom. So this is traveling a higher distance at the same time. That means the velocity in here is higher than the velocity of the wind below. Since the velocity is below, this pressure will be higher than this pressure. And the net effect in this case is the wing lifts up, because there is higher pressure from the below, because the air is moving slower than the pressure on the top, which the air is moving faster. So in this case, the wind lifts up. I mean, the wing will lift up and carry with it the entire plane. And that's how liftoff actually takes place. If you don't want that, if you don't want, for example, the object to lift off, you take the wing and put it backward. Okay, like for example, they do on the NASCAR cars. They put the wing backward. So in this case, the car stays on the track to get more traction, so that it moves faster and faster on the tracks. If you do it backward, the car actually will fly. So that's why you see them on NASCAR cars, for example, in racing, they put the wings backward, because they don't want the car to fly. They want it actually to stay on the ground. So this is actually one of the uses for the principle of Another one is the atomizer, for example, which uses for perfumes. The air is rushing in here from this one when you push on it with a higher pressure, and I mean with a higher velocity. So there is actually less pressure on this side than on this side, which brings the fluid now upward, which can be spread throughout. So again, this is in a nutshell your chapter. Remember, there are 3 questions today. The questions, the answers to them. The first one was basically, was it A? What is the answer to it? A, I forgot even the question myself. Downstairs, okay. That's where the fluid basically flows with which side higher. It's downstairs when it's coming from the same faucet and using just gravity. The second question is basically, why does the fish survive under water and we cannot? It's because it breathes the water. And the last question was, I forgot what the question was again. Can anybody remind me so that we post it in here?
It's the one with the 2 people drinking soda.
Oh, yes. So good thing. Thank you, Naomi. So soda in this case, the answer is no and no. No, they don't have necessarily to have the same amount of soda. And no, they cannot do the same thing on the moon, because there is no air pressure on the moon. Okay, see you guys on Thursday at 8:30. And the posting should be available for you, hopefully, whenever it is. But you should have the discussion open for you guys to answer your questions. Thank you.
Quick last question.
Go ahead.
Because I missed. Okay, so I wrote down all the questions that we did during the whatever we're doing today. I can't even think of it. Anyway,
Live
so the
session.
first question was the water one downstairs. Is that right?
Yes, the one downstairs should have more pressure coming off of it.
All right. I was thinking the lead question was the first one, but got it.
Okay.
All right. Thank you.
Okay, see you guys.
Okay, bye.
Okay, bye.